Hello, I just want to quickly run through the hydrocarbons and energy from fuels past paper questions that were set. Mostly it's question 2 in the multiple choice that I'd like to have a quick chat about. I will run through question 1 briefly as well, but I think question 1 was mostly quite well done. So 1A says name the elements present in a hydrocarbon. Careful, don't get mixed up and start using the information from the question here. Read the question carefully. It says name the elements. So it does say in the question there's a hydrocarbon mixture of isobutane, butane and propane, but of course these aren't elements. The elements in a hydrocarbon are just hydrogen and carbon. So hopefully that was nice and easy for you to get started on. 1B gives you a structural formula, and it says the full structural formula for isobutane is. So it gives you the structure here, and it says write the systematic name for isobutane. So mostly that was quite well done. A couple of you did get a wee bit mixed up in thinking that maybe it was asking for the shortened structural formula. So the shortened structural formula would be like this. That is not the systematic name though, so that's the shortened structural formula. Or you might have got mixed up and written the molecular formula. But again, that is not the systematic name, that's the molecular formula. So when you're asked for the systematic name, that's going through that process that we learned where you need to find the longest chain length and then number the carbons and name any branches. So this way we've got 3 carbons in a chain, this way we've got 3 carbons in a chain, so it doesn't really matter whichever way we go. We can call this one across here the longest chain. We can number the carbons in any direction. We could go 1, 2, 3 or 1, 2, 3 because the branch is in the middle, so normally we would number them to give the branch the lowest number or start at the end nearest the branch, but the branch is in the middle here so it doesn't matter. So we've got a branch with 1 carbon on it. It's on carbon number 2. And there are 3 carbons in the main chain. So the branch on carbon number 2 with 1 carbon we call 2-methyl. And the main chain with 3 carbons we call propane. Now actually, because there's only one possible version of methyl propane, if this branch was on the end it would just be butane. And we don't even need to put the 2 in because there's only one possible methyl propane. So either 2-methyl propane or just methyl propane on its own would be correct. Okay, if you weren't getting that, make sure you maybe do some revision on bite size or something like that. Look up Miss Adams' videos on naming hydrocarbons because it's really important that you can do that. Okay, part C. Alkanes have different physical properties, and the table gives some information about isobutane and butane. So isobutane has a boiling point of -12 degrees C. Butane has a boiling point of -1. So the boiling point of butane is higher. And you've got to circle the correct words to complete the sentence. So compared to isobutane, butane has a higher boiling point as it contains, I think this was pretty much universally correctly done here, it contains stronger intermolecular forces. So remember, with these molecular substances, if my hands are 2 molecules here, we're not breaking the covalent bonds within the molecule when they boil, we're just separating the 2 molecules apart. And so we're just breaking what we call the intermolecular forces. And the stronger the intermolecular forces, the higher the melting and boiling point, the more difficult it will be to break the molecules apart. Okay, question 2. 1D, this is one of the ones that people did find a little bit tricky, and there is a wee bit of a trick to this, so might be a useful one to pay attention to if you didn't get it. So we've got the table showing some boiling points of some alkanes, and we have to predict the boiling point in degrees C of nonane. So predict, when you see this predict, it's a really common type of question at National 5 and National 4 as well. And what you're looking for is you're looking for the trend in the data. So what's happening, how is it changing as you go along a series. So in this series here, pentane, hexane, heptane, octane, nonane, you haven't learned nonane, but hopefully you can guess that we're going 5, 6, 7, 8, 9 carbons. So we're going up in even steps here. And then we've got to think about what are the gaps between these numbers. So how much is the boiling point increasing by each time? So you need to get your calculator out for this. Don't just take a random guess. And so to work out the gap between 36 and 69, you're going to do 69 take away 36. So that's 33. And then to work out this gap, so we're going to figure out what's from 69 to 98. Okay, 30. And then from 98 to 126. That can't be 30. Hold on a second. What have I done here? 98 take away 69. 29. And then 126 take away 98. And that gap there is 28. So what you might be tempted to do, what I would be tempted to do, would be to take an average of these gaps, because it looks like it's going up pretty much the same each time, and then just add that on. But you've got to be a little bit more careful with this. The gaps, as well as going up by roughly 30 each time, the gaps are actually also decreasing slightly. So we go up by 33, then 29, then 28. So likelihood is that this next one is going to go up by 28 or less, because like I say, we started off by going up by 33, then 29, then 28, so the size of this number is getting smaller as well. So as well as looking at the general amount that it's going up by each time, you also want to see if there's any pattern. Are these numbers, are these gaps getting bigger, or are they getting smaller? So 28 or less, but it's not going to be significantly less than 28. So this one's gone down by, so you can maybe look at the next gap. So that one's gone down by 4. This one's only gone down by 1. So the maximum that this would go down by, I would say, would be could be 24. But let's go somewhere between 24 and 28, because I don't think it's going to have gone up by less than 24. So somewhere between 24 and 28. We could just say 26. So then we do 126 plus 26, and that gives you 152. Okay, so the SQA were allowing you anything between 150 and 154, which, so 150 would be if it went up by 24, and 154 would be if it went up by 28. Okay, so just do your best with these ones, but make sure you use your calculator to work out the gaps, and then look at whether the gaps are getting bigger or getting smaller, and how much by. Okay, question 2. Olive oil, which can be used in cooking, is a mixture of unsaturated molecules. State what is meant by the term unsaturated. Now, this might be my fault here, because I think a lot of you gave a definition that made sense but wasn't really the exact definition. You said what was meant, but really we're looking for a kind of chemistry definition which is slightly different to what a lot of you said. So a lot of you said that unsaturated means it can have more hydrogens added onto it. That is true, and I think I explained it in that way, but in terms of the definition of unsaturated, you want to say that it contains a carbon-to-carbon double bond, or at least one, but just containing a carbon-to-carbon double bond is fine. Oh. But you must specify that it's a carbon-carbon double bond, okay? Because if you have in some compounds you have a carbon-oxygen double bond, that does not mean that it's unsaturated, okay? So it's only if it's got a carbon-carbon double bond. A part 2, describe the chemical test, including the results that can be used to show that olive oil is unsaturated. We did this in class, the test for unsaturation. So it's the bromine test, or the bromine water test. And the bromine water, we say it decolorizes, and to be specific, we would say it rapidly decolorizes if the compound is unsaturated. The SQA will let you off if you just say decolorizes though. So bromine water rapidly decolorizes if compound is unsaturated. So you needed to say both things for 1 mark there. You couldn't just say the name of the substance. You need to say the name, describe the chemical test, and include the result. The result is that the bromine water rapidly decolorizes if the compound is unsaturated. Okay. 2b, when frying food, it is recommended that the oil is heated before the food is added. The table gives some information about olive oil used to fry food. So you've got the specific heat capacity of the olive oil, you've got an initial temperature, and you've got a mass of olive oil heated. So specific heat capacity is something that I expect you to recognise, and it has the symbol C. And you've got to calculate the energy in kilojoules required to increase the temperature of the oil to 180 degrees C. Now, when you see something about energy in kilojoules and you've got numbers like this, you're doing it tells you you're doing a calculation. There's only one option in chemistry that we've learned to do this, and we did it just before the holidays. So I can understand if you're a wee bit rusty, we didn't get all that much time on it. So you're using this equation here, EH equals Cm delta T, and I know that everyone should have that in their notes. So in this equation, EH stands for the heat energy, C stands for the specific heat capacity. So we've got, I'll do my data column down here, so C is 1.97 kilojoules per kilogram per degree C. So remember, C is the specific heat capacity of the liquid being heated. It's usually water that we use, but it's not always water. Okay, M is the mass of the liquid being heated again. So you should know what all of these symbols stand for. And again, I'm pretty sure they're in your notes. So the mass is 1500 grams. But because specific heat capacity is measured in kilojoules per kilogram, we have to convert that to kilograms. So 1500 grams, we divide by 1000 to convert to kilograms. So that's 1.5 kilograms. Delta T is the change in temperature. So the initial temperature is 20 degrees C, and we've got to increase it to 180. So the change in temperature is going to be 160 degrees C. So hopefully that makes sense. Once we figured all of that out, we're just substituting our values into the equation. So 1.97 times 1.5 times 160. Okay, and that's working out at 472.8 kilojoules. Okay, so energy is always in kilojoules as long as you put everything else in the correct units with this equation, because the heat capacity was in kilojoules per kilogram per degree C. If you want to round that up to 473, that's fine as well, but you would have been fine leaving it at 472.8. Okay, so make sure you recognise this type of question if it comes up again if you've watched this video. Right, last little bit, we're going to look at the multiple choice. The shortened structural formula for a compound is given here, which of the following is another way of representing the structure. So you did look at shortened structures, although no, we didn't spend a huge amount of time on them. So remember, if something is in brackets, that means it's a branch on the carbon to the left of it. Okay, so that's the trick to getting this question. But probably the best way to go about this one is first of all just to count the carbons, because that can straight away allow you to eliminate some of the options. And I would count the carbons in the main chain. So remember, anything in brackets is a branch. So if I count the carbons 1, 2, 3, 4, 5, 6, 7 carbons in the main chain, that's going to allow me to rule out some options quite quickly. So 1, 2, 3, 4, 5, 6, 7. Okay, that one's fine. 1, 2, 3, 4, 5, 6. Okay, it can't be that one. 1, 2, 3, 4, 5, 6, 7. It could be these two. So I've ruled out one because I know that there's only 7 carbons in the main chain. Another thing I can rule out is that my branches are clearly on 2 different carbons. So I can rule this one out straight away because this one has the 2 branches on the same carbon. So I can rule that out because these branches are on different carbons. And then I just need to look at where the branches are. So I've got, in the first one, in this shortened structure, I've got a CH3 and then a CH2 and then the carbon with the branch. In A, I've only got a CH3 and then a carbon with a branch. I don't have CH3, CH2. So I can rule out A, and that means the answer must be D. And that fits with my structure as well, because I've got CH3, CH2, carbon with a branch, CH2, CH2, CH3. So that fits nicely with D. Okay, question 4, identify which of the following is an isomer of this molecule here. So remember, isomer means same formula, but a different structure. You need to know the definition of isomer. So, rather, I should be specific if I'm giving you this. Same isomers are the same, have the same molecular formula, but different structural formulas. So if it's the same molecular formula, it means it has to have the same number of carbons and hydrogens. This is an alkane with 1, 2, 3, 4, 5, 6 carbons. It's not got any double bonds, it's just a normal alkane. So it's going to have CnH2n plus 2. So without even counting the hydrogens, there should be 14, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I can check that as well. So I'm looking for something with the formula C6H14. Now I can rule out A straight away because the cycloalkanes have the general formula CnH2n, so they are never going to be isomers of an alkane. Cycloalkanes and alkanes can never be isomers of each other. Okay, B is a tempting one. B looks like it might be correct, but the problem with B is actually B is just the same molecule as A, so it can help you if you're struggling with this to name the structure. If you're asked to find an isomer, it can help you to name, or at least to number the carbons, because remember, we number the carbons from the end closest to the branch. So this carbon, this molecule here would be 2-methylpentane. And if we look at B, if we number the carbons from the end closest to the branch, we can see that B is also 2-methylpentane. So if a hydrocarbon has a different structural formula, it would also have a same name. So something with the same name isn't an isomer. These two aren't isomers, they're just the same molecule but flipped over. So hopefully you can see that, if not from the structure straight away, at least by naming, hopefully that makes sense that those two, this one and B, are the same, so they're not isomers. D, I'm just going to talk about D briefly. D has the wrong number of carbons, so it can't be an isomer. So C is the only one that can be an isomer of this one up here, and C would be called 3-methylpentane, which just has the branch in a different position to the one in the example, so that definitely is an isomer. Okay, and then the last one was a nice quick one. Question 5 says, a student set up an experiment to determine the quantity of energy released when a hydrocarbon burns. Which diagram shows the apparatus that would produce the most accurate result? Well, again, we did this experiment in class. We used a draft shield to minimise heat loss to the surroundings. So you can see we've got two without draft shields, so straight away we can discount them. The other important thing about this experiment was that we used a metal can to maximise heat transfer from the flame into the water, because metals conduct heat better than glass. So the answer to 5 is B, and that's just a case of remembering the experiment that we did in class. So make sure you look back over that one. That's a key one that comes up in exams quite a lot. So make sure you revise that in preparation for any assessments. Okay, thanks for listening.